Data across global networks moves as a chaotic storm of light. At terabit speeds, millions of pulses fire down fiber optic cables every single second. But a raw flash of light is meaningless on its own. To turn those physical pulses into readable information, network hardware relies on a rigorous system of bit-level synchronization, logical addressing, and strict mathematical error detection. Modern switched environments operate at speeds that would have melted the original 10 megabit shared networks. Yet, the data traversing these new lines must remain perfectly backward compatible with legacy hardware. The mechanism that makes this possible is the Ethernet frame. We are going to mathematically and structurally construct a modern frame from the very first bit to the last, revealing exactly how it dictates the absolute limits of network performance. The precise arrangement of these fields governs everything from CPU bottlenecks to severe security vulnerabilities and total network failure. Before a network interface card can read a single piece of actual data, it has to physically align its internal oscillator with the transmitter's clock. This starts with the preamble. The sender transmits a 56-bit alternating sequence of ones and zeros, providing a rhythmic heartbeat. At high speeds, if the receiver's clock drifts by a nanosecond, it corrupts the sequence. Once synchronization is locked, the sender transmits the Start Frame Delimiter. Breaking the pattern with 2 consecutive ones triggers the hardware to switch into data reception. If that precise interruption is missed, the receiver cannot tell where the actual header begins. The frame is incorrectly parsed, causing immediate alignment errors. Following the synchronization header are the destination and source MAC addresses. Each is exactly 48 bits long, allowing switches to read the destination for routing, and the source to populate forwarding tables, a process called MAC learning. The IEEE assigns these physical addresses using strict rules. The first 3 bytes form an organizationally unique identifier, identifying the manufacturer, while the final 3 specify the exact network interface. The source MAC also provides the anchor for bidirectional communication. Protocols like ARP use these exact frame fields to map Layer 3 IP addresses down to Layer 2 physical hardware, allowing local packet delivery. During the early expansion of local area networks, enterprise systems like Novell NetWare developed alongside competing Ethernet standards, creating a major hardware compatibility problem. The conflict centered on the 2-byte field immediately following the MAC addresses. Ethernet 2 uses this field as an EtherType to identify the upper layer protocol, while IEEE 802.3 uses it as a length indicator. To resolve this, a strict numerical threshold was set. Values of 1500 or less mean length, while 1536 or higher indicate EtherType. But treating this field as a length indicator created a blind spot. To compensate, the 802.3 standard injects LLC and SNAP headers into the payload, shrinking the available user data space from 1500 down to 1492 bytes. That mathematical threshold allows modern network interface cards to process TCP/IP traffic alongside legacy storage protocols simultaneously on the exact same physical wire. As network infrastructure scale, dedicating physically separate hardware for sensitive broadcast domains becomes impossible. Engineers must logically isolate a physically shared environment. This is achieved by a IEEE 802.1q VLAN tagging. A 4-byte header is inserted directly after the source MAC address, increasing the overall frame size from 1518 to 1522 bytes. The first 2 bytes contain the Tag Protocol Identifier. Its fixed hex value of 0x8100 alerts switches that the frame is tagged, while the subsequent 12-bit VLAN identifier routes the data to one of 4094 possible logical networks. Because logical isolation relies entirely on these 4 bytes, misconfigured switch ports are highly exploitable. If an access port is left in a dynamic negotiation state, an attacker can spoof switch behavior to access all VLANs. Attackers can also execute a double tagging exploit using the native VLAN, which carries untagged traffic. By applying an outer and an inner tag, the first switch silently strips the outer native VLAN tag. This normal processing allows the hidden inner tag to carry the payload straight past network borders into restricted subnets. Modern enterprise security depends completely on proper tag handling. A single port incorrectly stripping or accepting these inserted bytes can collapse an entire logical perimeter. Inside the frame is the payload. For standard Ethernet, the maximum transmission unit, or MTU, is capped at 1500 bytes. This ceiling balances transmission efficiency with the mathematical probability of physical noise corrupting a large block of data mid-flight. When data exceeds capacity, the IP versions react differently. IPv4 allows routers to physically fragment a large payload into smaller pieces, doubling processing load. IPv6 prohibits router fragmentation entirely, rejecting the oversized packet and returning an ICMPv6 error. To prevent the heavy performance penalty of fragmentation, endpoints use path MTU discovery and maximum segment size clamping. During the initial handshake, hosts mathematically negotiate the smallest payload capacity along the entire route. But at modern interface speeds of 10 and 100 gigabits, the 1500 byte limit becomes a computational bottleneck. Moving that much data requires host CPUs to process over 8 million individual frames per second. To relieve the interrupt load on the CPU, administrators enabled jumbo frames, expanding the single payload capacity to 9,000 bytes. This drastically reduces the number of headers the hardware has to process. Jumbo frames lower CPU overhead, but they increase physical latency. More importantly, pushing a frame to 9,000 bytes stretches the traditional error detection mathematics of standard Ethernet to their absolute breaking point. Every frame concludes with a 4-byte frame check sequence. This field is explicitly designed to catch physical corruption that occurs while the bits are traveling across the wire. The hardware treats the entire completed frame as one massive binary polynomial. It divides this number by a fixed 33-bit generator polynomial, using binary long division and exclusive OR logic. The calculation begins with an initial value of all ones. This ensures that if a physical malfunction inserts silent leading 0 bits, the error is still mathematically caught. When the destination receives the frame, it runs the same calculation across the entire data block. Due to Galois field arithmetic, an uncorrupted frame will always resolve to a constant magic residue, exactly C704DD7B. This exposes the danger of jumbo frames. The standard 32-bit polynomial guarantees the detection of any 3-bit error, but only up to 1500 bytes. As the frame stretches toward 9000 bytes, the probability of multi-bit errors slipping past the math goes up exponentially. These errors are almost always caused by physical layer realities, degraded optical transceivers, dirty fiber connectors, or severe electromagnetic interference actively flip bits in transit. Tracking CRC errors is a critical diagnostic step. It proves the connection is physically active, but data is mathematically shredded by the environment before reading. Looking at the completed architectural model, the Ethernet frame operates as a masterclass in modular, extensible engineering. Every single transfer requires precise oscillator alignment, the seamless multiplexing of IP and legacy protocols, the enforcement of VLAN boundaries, optimized payload constraints, and strict galore field arithmetic. But as massive data centers push toward 400 and 800 gigabit links, the legacy 1500 byte payload limit and the standard 32-bit check sequence are proving inadequate for modern throughput demands. To compensate, the industry is forcing the adoption of super jumbo frames capable of carrying up to 64,000 bytes, relying on advanced forward error correction applied directly at the physical layer to maintain data integrity. Physical interface speeds will continually accelerate, yet the ability to architect resilient networks will always rely on a rigorous, bit-level understanding of the encapsulation rules that move this data across the wire.